Okay, so I will start my presentation. I slightly changed the title. It is now called Hybrid AI as Augmented PSE Techniques, and I will show you how we are integrating PSE techniques with AI techniques, with human intelligence, including what we learn from books, plus computers. So the motivation for doing this is that we humans are master of the planet Earth, but what should we do to remain at the top? We have the challenge of water, energy, food, and whatever we do with these resources, it affects our safety, health, and environment. So what we are interested in is finding truly sustainable solutions, and finding sustainable solutions means we are addressing these challenges. And I'm going to concentrate, or we are concentrating here, how we find the sustainable solutions with respect to synthesis, design, innovation of chemical processes as well as chemical-based products. So let me first introduce what we mean by synthesis. On the top left-hand corner, you see some building blocks that are the unit operations. And then in the figure next to it, you see a network. On the left, we have raw materials. On the right, extreme right, we have the products. And in between are the processing steps, which are represented by these unit operations. So the idea is which raw material should we use, which product should we make, and which path we should take. And the path at each step, which unit operation should we take. If we look at the bottom, similar to the unit operation, we have what we call building blocks or functional groups. That's a combination of atoms. And then we want to mix those atoms together to form a molecule. So the network is similar. At every column, we have to take one of those groups together and join them together so that they form a molecule. And we have to satisfy some chemistry rules. In addition to the groups of atoms, we could have chosen atoms and bonds. We could have chosen graphical neural network. All of these would be the same thing. We want to generate molecules and we want to see if they're chemically feasible. We want to generate flow sheets and we want to see if they're feasible. Having these flow sheets and the ones circled in red is a feasible flow sheet, and we can generate hundreds of them, but we are not going to design all of them or build all of them. We are going to build one of them. So we have to select one flow sheet or maybe a few promising flow sheets, but then we need to do the design of every equipment in that flow sheet. Design meaning design of the reactor, design of the distillation column, heat exchangers, and so on. And at the bottom, you see the molecules. We need to check what their properties are. If we want to use it as a solvent, do they match the solvent properties? If we want to use it as a drug, do they match the drug activities, and so on. So that's the design problem. And then once we have done that, we have a reference process flow sheet or a reference product that we can use. But can we improve it further? So that's where the innovation comes in. And the innovation is having the reference flow sheet that we see in the middle. Can we improve that flow sheet in different ways? And what you see is an intensified alternative. Similarly, if one molecule cannot give us the function that we want, we may mix the two molecules or more to form a mixture, and the mixture may be able to satisfy our requirements. And so we can therefore not only have pure compound products, but we can have blends, formulations, and so on. So these are then the three types of problems we are going to look at. We are not going to highlight solutions of many problems, but we are going to highlight the tools that will give us the solutions. So let's look at first problem solving with AI techniques as they are now. So we have listed some problems on the right-hand side. Knowledge is knowledge gaining, reaction path synthesis, then flowsheet, drawing of flowsheet, synthesis of flowsheet, design, innovation, analysis, control safety, and many more. And on the left, I've just listed a few tools, some of our tools, but also tools from that we can find in the industry as well as on the internet. So we have these tools. What kind of problems can we solve? So the question is, can the current generative AI algorithms solve these problems related to synthesis, design, analysis, innovation? And these are related mainly to the highlighted boxes that you see. And designing these kind of systems, such as chemical processes that are constrained by their control mechanism at various levels to ensure desired and safe operation throughout their life cycles, is a highly challenging task, because we have to satisfy certain principles that we cannot ignore. And those require more difficult kind of algorithms to solve. And so what we would say is in the domain of chemical engineering, the current generative algorithms or models are still in their development. In the meanwhile, we recommend agent-based systems, and that is what we will show you. But we are still using AI, not necessarily generative AI with large language modeling. So now let's look at a core function. A calculation of all of these is a simulator, whether we call it a process simulator or a product simulator. So what is the role of these simulators? In both cases, in the synthesis, we make a lot of decisions, and the role of the simulator is to verify whether those decisions are okay or not. In terms of the process synthesis, which unit operations we took, why we took, which raw material, which product, all those decisions that needs to be made, we can verify through calculations whether they were acceptable or not. It's the same thing with the product, which groups of atoms we joined, which kind of molecules we got, and whether those predictions are good or not. The thing to note here is that we are using simple predictive models because we have thousands, hundreds, and thousands of alternatives, and we need to quickly evaluate them. Next, we have a flow sheet. We want to design it in detail so that we can construct it. So these calculations now need to be quantitatively correct. So we need to use rigorous models so that whatever we calculate here can be built. And when it is operating, it will operate as designed. So here we again look at decisions that we have made during this design stage, and we verify this through rigorous models. Next, when we go to innovations, again, we are making some decisions, but now we are talking about hybrid multi-scale models. So what we see is that we are doing, the simulators have verification role, but the models and the functions they perform are different at these different stages. Another role is analysis, that we have done the generation, we have hundreds of flow sheets or molecules. We want to find very quickly which are the promising ones. So we need to analyze the results and find out through some matrix which are the promising ones. In the case of the design, we need to analyze the economics, the LCA, the safety, and so on to identify which would be the best design. In case of the innovation, we need to do the same, but now the models are different. So what we see again is Up to now, the simulation or simulator has both verification and analysis tools, analysis roles. So let's look at what the simulator does. You can see the main features of a simulator. If we have a process flow sheet already designed, already configured, and the red boxes indicate the input chemicals, the green is the output product. If we know all the details, we can perform the simulation and verify and analyze. But in order to get this process flow sheet, we needed to do the synthesis, we needed to do the design, we needed to do the analysis. If we want to replace this flow sheet with something more innovative, we need to do some innovation. So what we do based on all of this, we say that we have the product simulator, we have the process simulator. These simulators run on computers. These are trained by humans to perform simulations. And the techniques used to train are PSE techniques, AI techniques, many more. And then we have a pre-simulation activity and a post-simulation activity. The pre-simulation activity is problem definition, synthesis, design. That would give us the flow sheet we need, the design we need, so that we can do the calculation. Because without the flow sheet, the design, the models, we cannot do the calculations. So we have the pre-simulation activities. The post-simulation activities are the analysis, innovation, and others, control, and so on. So we have the pre-simulation activities, the post-simulation activities. What we see is that most of the time is spent on the pre-simulation activities and post-simulation activities. The simulator itself, if the problem is defined well and all the tools are available, we can get the solution quite fast. So now with respect to the process simulator in the middle, we have pre-simulation activities, we have post-simulation activities. Based on these ideas, we have developed a workflow, which is a 12-stage workflow. The first stage, 3-stage, 12 steps. The first stage is the synthesis stage. We define the problem, and then from steps 2 to 5, we find out what are the important promising flow sheets. Once we have that, then we perform process design in step 6, and then we perform simulation. So you can see that the simulation here, the simulator, as we know, is step 7. Before, all the simulations are with other kind of simulators. Then once we have the simulation result, we do the analysis. Summary here is telling, based on the analysis, what could be the targets for improvement. And once we set up the targets, we try to find, through steps 10, 11, 12, alternatives that match the targets for improvement. And by definition, any alternative that matches the target would be a better solution than the one that we have. So a more sustainable solution. So this is the workflow. And what I will show now is, for this workflow, what kind of tools we need and why we call it an agent-based system. But before that, let me introduce some concepts. We have 3 main parts: synthesis, design, innovation. What is the concept for synthesis? We look at synthesis of molecules. Again, I'm using functional groups, but they could be atoms and bonds. They could be GNN, graphical neural networks. We combine them to form molecules. We represent the molecule with a SMILE string. And then if we have a model that you see in the equation, we can calculate the properties. And the model would be the contributions of the groups and some regress parameters that will give us the properties of the molecule or the mixtures of molecule. So now the question is, can we do the same for process? If we can, then we are combining what we already can do very well in terms of molecular design and mixture design, and we combine it with process design, so we can solve this problem very, very fast. Note that we can generate hundreds and thousands of molecules and calculate their properties within a few seconds. So we have defined something called process atoms. So it can be input atoms, it can be output atoms, chemicals that come in, chemicals that go out, and it could be a reactor atom where A is converted to B and C, and A is not 100% converted. So that's a reactor atom. And similarly, we have separation atoms. F indicates a flash, D indicates a distillation, M indicates a membrane. So we can define a lot of these atoms. And then if we have a collection of these atoms using the same rules as the molecules, we can generate a process flow sheet. And note that in this flow sheet, all the chemicals are traced. A from the point where it enters and the point where it goes out, or B or C that is generated, these are all shown in that flow sheet. And that flow sheet then, just like the molecule, is represented by what we call a S-file. An S-file keeps track of all the chemicals going through as it enters and leaves or as it is generated, and which operations are using them. And if we have this S-files representation, and if we have the parameters for all the atoms, process atoms, we can also use the same type of equations to calculate the properties of the flow sheet in terms of how much energy it uses, how much, what is the carbon footprint, what is released to the environment, and so on. So now we have combined the synthesis concept for molecules and processes with the same method. Then the design. In the case of molecules, we do what we call the reverse of the property prediction. We know the molecule, we use a model to calculate the property. But in the design, we know the property. What we want to know is which is the molecule. So it is the reverse of the property prediction. And we use exactly the same idea for process design. I'm showing just an example of distillation column. On the left, you see a curve. That's the driving force curve that is calculated from the vapor-liquid phases that are in equilibrium or that are in coexistence. And if there is no azeotrope, then there is a well-defined maximum point of the driving force. And it is known that if the driving force is large, the separation would be easy and will require less energy because energy is needed to create the vapor liquid. So if we have this diagram, which we can easily obtain without any simulation, we identify the diagram, we identify the maximum driving force point, and then we know which product purity we want at the top and purity at the bottom, and we can do the reverse design here, finding out what the feed location is, number of stages, reflux, and all of that. So having these two, and we have a step-by-step method. So this is the reverse design. We can do that for reactors, for separators, for heat exchangers, all of those. So then that is the reverse design concept. And finally, the innovation concept. It's a multi-scale approach. And the idea is that we start with our reference process, and we break down the reference process going to smaller and smaller until we cannot break down anymore. And this is the phenomena at the right. Once we have this phenomena, then we combine the phenomena to form tasks, the tasks to form operations, the operations to form modules, and the modules to give us a flow sheet. And the flow sheet that we get, if they give us the same product, same specifications, but they have to be better by at least 20% or something in terms of energy, in terms of CO2 emission, and so on. And then we have a new innovative alternative. So this also can be done in the same way that we find mixtures, and we will find also flow sheets. So if we go lower in scale, let's say if we have 3 molecules, and if we want to find a binary mixture, we will have only 3 binary mixture. If we have molecular groups, we can form more molecules, we will have more mixtures. If we work with atoms, we will have more molecular groups, more molecules, and therefore more mixtures. So exactly the same idea we will do with the flow sheet. We have a flow sheet with 3 operations. We can combine them in different ways, but not too many ways. But if we break down in terms of operations, as I said, 3 operations can give only 3 maximum, or a few more if we do not satisfy all requirements, flow sheets. But if we break down the operations into tasks and how many ways the task can do the operation, we will get more operations, and therefore we will get more flow sheets. And if we break the tasks into phenomena, we will have different combinations of phenomena doing the same task, different tasks doing the same operation. And so we will have chance to get more flow sheets or more innovative alternatives. So this is the 3 concepts that we are applying in our algorithms and methods. So we talked about the approach with respect to the roles. We talked about the concepts. Now I will briefly mention a few tools. And the first most important tool is the model. We need model. We need to develop these models very fast. We need to be able to have a big model library and reuse in different ways by adopting the model for different purposes. What you see in the figure is that there are some parts the human can do, some parts the computer can do, and if we can combine them in a good way, then we can save nearly 80% of the time needed to develop new models. And by models, I call all kinds of model types that you see below. Once this gives us a model, we can say that this is a model object. We can export to other environments. We can keep it in a library, or we can use it to develop systems for synthesis design, and all of that into integrated systems. And all of these days, with the help of AI and some other computer science tools, we can develop all these integrated systems without the user needing to write any code, programming code. But the user needs to understand the problem, needs to understand what they're doing, but they don't need to do the coding. So there is a lot of saving in time and resources. That's the model. But working with the chemicals, one of the problems are that at this moment, if you look at the databases like PubChem or CAS data, you will see that there is more than 100 million chemical structures already generated. But do we have the data for them, measured data? Not really. It's less than 100,000 for which measured data is available. So all those molecules, we need predictive tools to as accurately as possible, do the calculations and fill up the gaps. So we have developed what we call a pure PML. This is a machine learning based tool for predicting pure compound properties. And what you can see on the screen is that we can give very accurate values, and also for properties for which there is no measured data. So we can fill out with this tool all the requirements for missing data. And this can be done for large molecules. And we can see also the performance of the model. On the y-axis is the error, relative error. On the x-axis is the individual data points. And we can see that in order to reach, for example, 1% error, nearly 90% or more of the data is predicted with accuracy of 99%. So that's very accurate model. But these are for what we call large molecules, and it's not applicable for refrigerant or small molecules. So we have developed another model for refrigerant molecules with another set of parameters, another set of atoms and atom bonds and groups. So that's the pure PML. It helps us to fill up the gap for the pure compound properties. Then we have the mixtures. Very often we come across that we want to design a process, but we don't have the mixture data. And how can we then do the calculation, because the models require mixture-related data. So we found that the Cosmo tool or Cosmo-based methods predict the phase equilibrium very accurately or reliably, I would say. And we could then use these as the pseudo measured data and then feed those generated data to the engineering model so that we can do the calculations. So here is an example. The Cosmo model also needs the sigma profile. So we have put in a database with, at this moment, close to 3,000 molecules for which we have the sigma profiles, and we are continuously increasing it. And then we generate the data. This is SLE data. And then once we have this data, we feed this data to Unifac, Uniquac, and all that. And so we can do the calculations very fast. So now all of these tools of process systems engineering, of AI, we mix together and we have the hybrid AI. And here, AI is handling the complexity. Computers are handling the problem size and speed of solution. Problem solution, numerical solvers and machine learning tools are giving us robust solution techniques. And then we humans, we glue everything together. So we have a role also. And all of this we have put together in what we call ProCFD. It's a complicated diagram. We don't expect you to read anything inside. But what I'm pointing out is the 12 steps. Step 1, then 2, 3, 4, 5 is the flow sheet. We can skip all of that if we have a flow sheet and start from 5. Then we do the design, 6. Then 7 is the simulator. Then 8 and 9 are analysis, and 10, 11, 12 are innovation. So what do we have? So you can see AI guides the user to define the problem. And also in definition of the problem, we need some databases. In doing the synthesis, we need a collection of databases, collection of models. Selector means decision making. Generator means an algorithm that will generate all the alternatives. Evaluator means that we will use model to rank which is the best flow sheet. Then we will do the design in step 6. We will go to the simulator. And then this is the step 7 where we need the simulator. After that, the simulation results are used to analyze like LCC, safety, cost. Then based on these, we will set the targets. And then through integration, intensification, optimization, we will find alternatives that match. So these are then the tools here and here, which we call agents. And the ProCFD interface knows at which step which tool is needed and which calculation needs to be used and which data needs to be used. And that's why we call it agent-based approach. So I will quickly show you some screenshots, but later on, the Thai team will present the ProCFD. Here is the kind of flow sheet that you can see in the form of a graph. This graph is a superstructure of all alternatives for a separation of 5 compound mixtures. But we are using hypergraph. Hypergraph means that it not only shows the diagram, but it also gives data, stores data within the hypergraph. So at every node, that is the stream in the flowsheet, and every connection between two nodes is a unit operation. And these are vectors with a lot of information in there. The blue is the inlet, the green is the chemicals that needs to be recycled, yellow, orange is the products. So then we know immediately the green needs to be recycled, the blue is coming in. If it goes out, it will be wasted. The orange are the products we need to store. I told you about the synthesis, that we can generate the molecules or the mixtures very fast, flow sheets very fast. So here is an example for the HDA process. Hydrogen and toluene react to give benzene and biphenyl. So with that, and then methane comes in as a inert. How many process flow sheets can we generate? Within a few seconds, we generated 340 flow sheets. Every flow sheet from the S file, we can look at the drawing of the flow sheet. We can look at the hypergraphs with the associated data. If we only say we want data data related to or flow sheet using distillation columns and vapor liquid separation, it turns out there are only 10 flow sheets. And then we rank them in terms of energy use, carbon footprint, product output rate, and so on. And these calculations are done not with simulation, but with what we call flowsheet property models. And these property models can be generated simple, or we can generate with machine learning. Once we have got the flowsheet, then we do the design. And then after the design, we create the input file for any process flowsheet we would like. At this moment, we have access to Pro2. So we have generated flowsheet inputs for Pro2. This means that the user does not have to write any or create the input file for the simulator. The tool will create the input for the simulator and call the simulator. And then it will do the simulation. Once the results are obtained, these results will be passed back from the simulator, and then it will do the analysis. So what you see again is a hypergraph, and each node in the hypergraph is the stream, and you have the data for that stream, and each connection between the nodes is an operation, and you have the data for that. So it's very easy to, with the hypergraph, to not only show the diagram of the process, but also the accompanying data. So if we store these hypergraphs with the data, we can open them anytime. We can run the simulators and all these things much easier. And I will just skip these. And then, so at this point, let's say that we have the flow sheet, we have done the analysis, and we have found out that there are some targets by which we could improve the process. So what you see is the HDA process again. This is the flow sheet that has been optimized, but can we improve it further? Or can we can check whether we can intensify it to a reactive distillation. So are we going to spend a lot of time doing a lot of calculations to find out whether it is possible or not, or can we do some shortcut? So what we have developed is a kind of a rule-based method, but these rules are based on actual data. And the approach is that if the answer to all these questions is yes, it cannot be maybe, it has to be yes, then the process that is being shown can be converted to a reactive distillation. How do we answer that? Because we already have the results from the simulator, and these are needed to answer this question. For example, is the reaction exothermic? Is there only one reaction? And so on. Are there isotopes? So on. So if we look at the results of HDA process, we will find out that not all the answers are yes. So reactive distillation is not possible for this. On the other hand, if we take the methyl acetate production, methanol plus acetic acid reacting to give methyl acetate and water, this is the flow sheet that have been built, Eastman Kodak process from the 1960s, I think. But they also found the alternative reactive distillation. But how did they find out? That's another question. But our tool will tell whether it is possible or not. So if we ask the 7 questions again, using the simulation results that we have, all the answers are yes, meaning that this process can be converted to reactive distillation. So I show you the 7 questions. It is yes. So we now combine reaction and separation together. So 2 atoms combined together give a molecule. So reactive distillation is combining reactor atom and a separator atom. So A and B come in, A, B, C, D go internally is produced, and then C, D go out. So then we have a model for it, and then we can do the design and we can confirm that this is indeed possible, but not only possible, it gives much more than 20% improvement in terms of material, in terms of energy compared to the original. So that's the innovation part. Then I come back to the question, how can generative AI with trained LLMs, large language models, solve the synthesis problem? And there are examples that say that we can give a reactor followed by an absorber, and can we complete that flow sheet? So I would say that this is like asking to autocomplete a sentence, I want A, and then ChatGPT or others should complete this sentence. So what would be the answer? It would be millions of alternatives. So ChatGPT or others will say, I need a context. So I want A, for example, a car. Then there are lots of data about cars, and by asking different types of questions, what type of car, what type of engine, all of that, one could come to a solution. But all the data of the cars are available, so one can find a solution. That's perfectly all right, and a lot of applications are like that. But if I say I want a friend, now friend is a person, a people, and it is almost all the people in the world. So again, if we say context, we can reduce and reduce and reduce, but still it is people, and not all the data of people are everywhere that one can put in a large language model. There are still data that needs to be studied, measured, and maybe modeled, and then after that it can be solved. So this kind of problem is also what I would say is trying to solve this. We have a reactor, we have an absorber, it seems, but we don't know how many compounds are coming out. And if we autocomplete it, and we get these 2 and hundreds more, in fact, all flow sheets with a reactor and absorber are valid for this autocompletion. But which one is correct? Is the first one correct, or the second one correct, or none of them? Because the context is not known. We do not know how many chemicals come out. We do not know what the reactions are. In order to find out after the reactor what will happen, we need to know how many separation steps, meaning how many compounds. So, which reaction? And then we can see the first reaction, A going to B, is certainly not feasible in this case. A going to B plus C is possible, but the last 2 are also not possible. So does it help anything? And also, if we are going to use distillation columns, as are shown in the flow sheet on the right, in order to know whether distillation column would be used or not, we need to know which chemicals are involved. Not only A, B, C, but actual chemical, because the actual chemicals and their properties will tell us which separation technique. So in our method, that's why we say we want to know the chemicals, we want to know the reaction, then we can autocomplete. Not only with one or two, we can generate all possible alternatives through our method. And we actually, in our library, save all the S files. So anytime we can generate all of those needed. So in my opinion, this is not actually a good problem to solve. It's a waste of time. Similarly, we can say with respect to the product, if we are trying to optimize, and many of the claims are that they have optimized the product with one property, but it is seldom that one product is defined by one property or one function. If I put two functions, the optimal solution may change. If I put three functions, the optimal solution may change. So claiming that they have the optimal solution with one product, it actually also is a waste of time. But here, the generation of alternatives is not a problem. As I said, there are more than 100 million structures already available in these databases. What is needed is the correct formulation of the problem and the accurate prediction of the properties. So with that, I will go to my last topic. So here I was actually looking at a separation book, and every separation book gives this ternary diagram and residue curve map. Is acetone, chloroform, methanol, and there are 4 distillation boundaries. They talk about all the difficulties of this and how complex this system is, but nobody gives how to separate them. There is no books that tell how to separate them. I checked also on the internet. They give the same thing, very difficult, but no solution. So we said we will try to adopt this problem and find out how to solve it. And how to solve it is that if we look at the binary pairs on each side, and if we can find a solvent that will selectively take the compound at the top, chloroform, and not acetone and methanol, then we can remove chloroform from the system, and then we have acetone and methanol. So that is one way. So how to take one compound out, which would leave the other 2 compounds with its azeotrope, but that azeotrope is easy to separate. So if we can find a way to remove one compound so that the other 2 compounds are easy to separate, one would be by distillation, by solvent-based extraction. So we need to find a solvent. Another could be to use a membrane to take one compound out. So if we take one compound out, there will be only 2 compounds left with one azeotrope, and it becomes a very easy separation. So if we take chloroform out, then acetone methanol is remaining. It turns out to be a pressure-sensitive azeotrope, and pressure swing distillation is possible. So we asked for just for acetone chloroform, ChatGPT, Gemini, you see in gray and blue, the problems. They all said it's difficult. They said it's azeotrope, but it's a high boiling azeotrope. They said it's a low boiling azeotrope. Maybe now, after a few trials, it has found out, and it will say now it is a high boiling azeotrope. The azeotrope point is given correctly, but ChatGPT says use azeotropic distillation. Gemini says fractional distillation, but it is actually solvent-based extraction. Again, the internet results are benzene, whereas a good solvent known is DMSO. And the design method is very vague, but here at least the design method is well known. So we find the good solvent, DMSO in this case, happens to be quite good. So we can extract chloroform, and then we have the flow sheet on the left to extract chloroform, and flowsheet on the right is pressure swing distillation. All of these can be done through hybrid AI SEP. And hybrid AI SEP is a kind of a chat interface based tool, but it does generate data, not only fixed data that is in the database, but generates data, uses tools to do calculations, which tools based on LLMs will not do. And you will see a demonstration of this from the Thai team. Finally, I will end by saying that PSE provides the glue to integrate different methods, tools, data, etc., for solution of a wide range of problems. And it integrates also AI and disciplines, but we need to do more in novel materials. We need to find new catalysts, membranes, adsorbents, solvents, refrigerants. So this is how to address the problem of food, water, energy, safety, health, environment. We need these in the smart manufacturing, in the sustainable energy, in the healthcare. We need to, if we understand the problem, formulate the problem correctly, use the right tools to solve these problems, we should be able to address this and find these solutions and make these developments. Thank you very much. With this, I will end. And I will stop sharing my screen. And before we go to the next presentations, if anybody has one or two burning questions, I can take it. Otherwise, the next presenter will be Chris, and Chris will start soon. Let's see if there is anybody who wants to ask any question.
I think there are two questions in the messages.
Oh, okay.
I see this.
So you tell me then the questions, please.
Okay. The first one is from Emmanuel Agunloye, and the question is, can we revisit this presentation? So I think the question is, how can we see it once the demonstration ends? And the second question is they're asking how they can access these tools.
Okay, the first question, we will put the recorded videos on our YouTube channel, so you can see them through the YouTube channel. And the PowerPoint files in PDF form will be on our website. You can download them. Okay? And the question about how to access them, if you are an educational institute, you can contact me and we can see if we can help you with a education license. If you are from industry, we need to find out what would be the good license agreement. Okay?
I think both of these replies, are clear. Do you have any further questions to Professor Gani?
Hi. Hello, Professor Gani.
Yes.
I got a question. So basically, when you talk about the process simulation, as we know, thermodynamics is kind of fundamentals for the process simulation. What's your perspective for the AI or large language models on the thermodynamics to accelerate the process simulation or optimization?
So I gave you two examples of tools. These are the first one. We use not large language model. We used machine learning. We have data, collection of data. Using machine learning, we got accurate model. I don't think large language models can do the prediction that we are doing. For the second one, Cosmo is not large language model or it is not machine learning. It's there are some people I know who are developing models like that, but it is I would say maybe another 5 to 10 years, maybe there would be models like that. But at this moment, I think Cosmo is the safest option. But we
Okay.
can discuss it later. I don't want to stop the other people who are supposed to present. So
Okay, great.
let's stop the discussion now, and we will come back to your questions later. So Chris will start now. Chris.
Thank you, Professor Gani.